Hey guys, today we're going to start Chapter 3. Chapter 3, we're going to focus in on some particular functions. We're going to start with linear functions. So all the problems you're going to see today, the functions are going to be like x to the first power, so that's linear. And then the next class, we're going to move into quadratic, so the x will be to the second power. And then eventually we'll get to what are called polynomials, where x could be to the third, fourth, fifth, whatever. So this unit is going to build. Okay, so it's going to start off very basic, very easy, but it will get challenging by the time we get to the end of it. Okay, so first off, a linear function is a function of this form. This would be in what is called slope-intercept form, where the m is your slope and the b is the y-intercept. The domain would be the set of all real numbers. There's no fractions, there's no radicals, so we can plug anything into that. The range would be also all real numbers unless there's no slope. So if you have a constant, which would technically still be a line, then that's going to have a different range. So if you have y equals 2, then that's just going to have a range of 2. But normally, if we have some kind of slope, no matter what it is, positive, negative, whole number, fraction, whatever, then your range is going to be all real numbers. Okay. So for example, this function could be graphed. I would start with the y-intercept plus 1. And then the slope is -3/2, which means this graph is going down 3 units for every 2 units that it goes over. So 1, 2, 3. Then I'm going to go right 2. And then I'm just going to connect those 2 points that I've created. I could also go, what did I go? Down 3, right 2. I could also go up 3 and then left 2, and that'd give me a third point even. But to the best of my ability, I'm going to try to make somewhat of a straight line out of those. Okay? So that is the graph of that function. The domain and range, well, you can easily tell that the domain would be all real numbers, and the range is also all real numbers. Okay? Now, given some information, and this is something we're going to do today, and we're going to do on another lesson as well, how can you tell whether or not you have a linear function? So, meaning you would have a line. Well, to have a line, you need to have a constant slope. So right here, we're going to talk about what's called the average rate of change. So linear functions have a constant average rate of change. Things are changing constantly. Okay, there's no fluctuation in how fast or how slow the information is changing. So average rate of change of a linear function looks like this. That little symbol right there, it's called a delta. It means the change of. So the change of y's over the change of x's is your slope, and that should be constant. In Algebra 1, you would have seen y2 minus y1 over x2 minus x1. And that's all we're doing. We're just kind of calling it something different. Okay, it's called the average rate of change, and that's your slope. Okay, so look at the first problem here. It says a strain of E. coli is placed in a petri dish at 30 degrees Celsius and allowed to grow. So the data in the table is collected. So use the average rate of change to determine whether the function is linear. So as time is going by, so at the start of the experiment, there is 0.09 grams of this bacteria. And then after 1 hour, after 2 hours, after 3 hours, they're calculating how much is in it. So we're trying to decide whether or not this is a linear function. All right, so calculator time. If I look at these 2 pieces of data, and I subtract the y's, so 0.12 minus 0.09, and that's going to give me 0.03. So there's my change in y, 0.03, over my change in x. Well, that's just 1 minus 0. That's the change from the first hour, or from the 0 hour to the first hour, we'll say. Now, let's look at this one. So 0.16 minus 0.12 is going to be, I thought I said that wrong. 0.16 minus 0.12, and we're going to get 0.04. 0.04 over, and again, over 1. We can stop right now. The fact that these two slopes between the 2 points are different, that means this does not have a constant rate of change, and this is not linear. Okay, let's put it right here. Not a linear function. Okay? Over here, we've got some data describing age and the maximum number of heartbeats per minute. Okay, so again, let's check. I'll move over to here. All right, so here's our points. These are the ages are going up. The heart rates are actually going down. As you get older, your heart rate kind of slows down a little bit. Okay, so let's see what's going on with this data. So this average rate of change, so 47 point. Now, and you can subtract in either direction. Okay, as long as you're consistent. I have a tendency to always do the second point minus the first point. It's that algebra y2 minus y1 that's just kind of stuck in my head. So I'm going to subtract 47.5 0.5 minus 50, and I'm going to get negative 2.5 over, and then 30 minus 20 is 10. And then I'm going to look between these two. I'm going to get 45 minus 47.5, which is again negative 2.5. And again, this is a change of 10. So we can see all our x's are going up by 10, 30, 40, 50, 60, 70. So as long as these are always going down by 2.5, which from 45 to 42.5 is a change of 2.5, and then it goes down another 2.5, and then it goes down another 2.5. So all of these values are going to be the same. They're all going to be negative 2.5 over 10, which typically you don't leave fractions with decimals in them. But for this, we're just trying to see if these values are all the same. So yes, this is linear. Okay? All right, on the back, we're going to talk, again, you're going to be hearing these words, increasing, decreasing, constant. Now, with a linear function, it's pretty straightforward. If you have a positive slope, then your graph is always increasing over its entire domain. If you have negative slope, then the graph is decreasing constantly, always. And if you have zero slope, if you're a flat line, then your graph is always constant. So lines can also be increasing, decreasing, or constant, but it's consistently increasing or consistently constant. There's no change like some of the other graphs we looked at in Chapter 2. So look at the following. Are the following linear functions increasing, decreasing, or constant? And then we're going to answer some questions about those functions as well. So right here, I can see that the slope is negative 2, so this graph would be going down. So this is a decreasing function. G of x equals 7, so there's no change. That is a constant. And then 4x minus 1 has a positive slope of 4, so it's always going up, 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 up. So it's increasing. Okay? Now, given those functions, we're going to ask some questions about them. Like, for example, solve f of x equals 0. When does that function equal 0? Well, if I replace the f of x symbol with a 0, 0 equals negative 2x plus 5, I can solve and find what x value will create a 0 in this function. Well, if I move the 5 over, negative 5 equals negative 2x, so x equals negative 5 over negative 2 is going to be positive, and I'm just going to leave it as 5 halves, and that's good enough for me, or 2.5. So that would be that'd be like your x-intercept of this graph. Okay, because that's when the function equals 0. So you're sitting on the x-axis. Now this one says, what is f of 0? So that means, what do you get when you plug a 0 into this function? Well, this term with the x is now going to get canceled, and you're just going to be left with the positive 5. So f of 0 equals 5, which is your y-intercept. Okay? So determining when the function equals 0, that's your x-intercept. And then figuring out what f of 0 is, what do you get when you plug a 0 in? That would be your y-intercept. Okay? For example A, what is f of 5? What do you get when you plug a 5 in? Well, looks like I would get a negative 10 plus 5, so negative 5. Okay, so that's just a random point that would be on that line. G, solve h of x is greater than 0. Okay, so when is this function, 4x minus 1, greater than 0? So when is that function positive? That's literally what this is saying. Well, if we solve, 4x has to be greater than 1, x has to be greater than 1/4. So whenever your x value, your input, is greater than 1/4, then that function is going to be positive. Okay? Last one. When solve fx equals hx. When do those two functions equal each other? This is going to be important at the very bottom of this page as well. Well, if I take these two functions and set them equal, so negative 2x plus 5 equals, and then 4x minus 1. And then I could just solve for x, and that would tell me what x input value has the same y value for both of those functions. So I would move the 2x to the other side, and I would move the minus 1 to this side. So it's going to give me a 6, and it's also going to give me a 6x, so x equals 1. So when x equals 1, those two functions have the exact same value. All right, we've looked at a lot of graphs so far in this course. So this is an example of a linear function. So this is g of x. We've got some values on the function that they've given us, and we're just going to answer some questions that we see over here. So for example, solve g of x equals 20. So when does the function, so for what x value does the function equal 20? Well, we've got the point 520, so x equals 5. That's it. Okay, that's what we're doing. Okay, when does solve g of x equals 60? So x equals negative 15. That would be the solution to that. Solve g of x equals 0. When does the function equal 0? Well, that's at 15, so x equals 15. I know, we're going pretty quickly here. Solve g of x greater than 20. So when is the function greater than 20? Well, here's 20. So when x is 5, the function is greater. Well, when x is 5, the function is equal to 20. We want to know when is the function greater than 20. So that would be all of this over here. There's a couple ways to look at this. We could say the function is greater than 20 when x is less than 5. Okay, because these are like negative x values that are giving us all these values. We could also look at this the way we've been talking, like looking at it as an interval. When x is anything from negative infinity up to 5, but not including 5, it's equal at 5, not greater than. So anywhere on that interval, these are your x values that are going to create a function value that's greater than 20. Okay? So going with that, look at the next one. Solve g of x less than or equal to 60. So that's when the function is equal to 60. I want to know when is the function less than or equal to 60. Well, it's equal to 60 at negative 15. And then the graph is going down, 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 down as my x's are getting bigger and bigger and bigger. So if x is greater than or equal to negative 15, the function is less than or equal to 60. So we're just kind of visually solving these questions by looking at this graph that's been given to us. Okay, we're just interpreting a graph. All right, solve. When is the function between 0 and 60? So 0 is less than g of x, which is less than 60. All right, so here's 0. So when x is 15, the function is 0. And then at negative 15, the function is equal to 60. So when is our function between these two values? Well, when x is between negative 15 and positive 15. And that's it. That's all we're doing on that. All right, and then lastly, we've got this little example of a story problem that involves linear functions. So let's go ahead and just take a look at this. So a quantity supplied of a good is the amount of a product that a company is willing to make available for sale at a given price. The quantity demanded is how much, people want that product. So what we have down here are two functions. So this is a supply function and this is a demand function. Okay? So what we're looking at are two functions, supply and demand, and I'll kind of sketch this so you can kind of picture what's going on here. So we've got a certain price. So this is like for a cell phone. Okay, so these are the formulas for this cell phone. So you'll notice the supply function has a positive slope. So as the price goes up, the supply is going to go up. Okay, if the price is 1,000 or 2,000, or as the price goes up, the company's going to say, hey, we'll make more and more and more of these because we want to make that money. But at the same time, you'll notice the demand function has a negative slope. So the demand is going down. So this is supply. So S of P. And then this is D of P. So the demand based on the price and the supply based on the price. And those two are going to cross at some point. So the equilibrium price of a product is where these two lines hit each other. Okay, so where are they equal? Well, if we simply just take these two functions, so 60p minus 900, and set it equal to negative 15p plus 2,850, and solve that, we'll find the price at which these two things equal each other. Okay, so if I add 15 over here, so that's now 75p. If I add 900 to the other side, so that's going to be 3750. And then grab your calculator. No need trying to figure out 3,750 divided by 75. Oh, it's 50. So P equals 50. All right, so that is the equilibrium price. If they sell the cell phone at $50, the amount that people want versus the amount that the company is willing to make will be justified, will be equal. There won't be any left over, and there won't be some huge shortage of them. Okay. What is the quantity demanded or supplied at this price? Well, the reason I put this or supplied is because they're going to be the same. So that's the equilibrium price. They're going to cross each other. So the quantity demanded. So if I look at the demand function and put 50 in for the price, negative 15, and then times 50 plus that 2,850. So negative 15 times 50, and then plus 2,850, 2,100. So that's the amount that would be demanded. Okay, that's it. Take a look at your homework. There's a couple story problems. There's a word problem like this. So use this as an example. I do ask a couple like extension questions based on kind of this little picture that I drew. So you can look at that when you get there.